Hi, I'm Dave Brady. I want to talk to you today about a paper that I recently posted on Archive with my collaborator Greg Nero. The paper is called DenseHolographicAssociativeMemories. The origins of this kind of work go way back to the 1950s. Here's work by Raymond Burrell on the idea of neural processing by wave propagation through a mass of cells. Burrell was an electrical engineer. He worked later at the University of Nottingham, where he founded the electrical engineering department. He never worked really on this kind of work again. He later worked in image science. But here, for some reason, he became excited about the idea that wave propagation was fundamental to the processes in cellular networks. And in this figure 16 and 17, he seems to suggest holographic memory, that he shows waves A and B propagating through a mass of cells, and then when wave A is present, it regenerates wave B. This idea that processing occurs through brainwave propagation continues even to this day. You see at the upper left a recent paper on cognitive processing through some sort of wave dynamics in the brain. In Burrell's case, I don't really see the link to neural processing. He's thinking of something way in the future that it's an interesting idea, but how it relates to the way cells really work, I don't understand. You see a lot of work in the 1950s and 60s that was highly speculative. And Burrell's work, for example, then inspired Peter van Heerden, who in 1969 published this figure showing a optical intelligent machine where somehow senses and moods come in from the left, and they're transformed into optical signals that are then processed in three-dimensional holograms and go out to a camera tube. This figure is from Van Heerden's book, The Foundation of Empirical Knowledge with a Theory of Artificial Intelligence, which is quite an aggressive title. Some of the results in Van Heerden's book also seem to indicate future ideas for compressive measurements. So he was, way ahead of his time. The time that he proposed this, the materials that he would use for volume holograms and the modulators and detectors needed to do this didn't really exist. But it inspired a number of other researchers to be excited about this. For example, Dennis Gabor in 1969 published this paper on associative holographic memories. The little spinning discs you see here are film rolls, so he suggests recording associations between patterns A and B onto a film roll, and then by inputting A at the right time on the film roll, you can regenerate the signal B. So this was in 1969, and then not much happened for the next 16 years. Gabor himself somehow thought that physical design was at an end.
I'm myself a physical inventor, a passionate inventor, and I'm very well aware that I'm one of the probably last generation of physical inventors. Of course, we still need inventions, but we don't need very much in terms of physics. Biological inventions we still need. Cancer is still something we must get rid of. But after that, what is important, the creative minority must put their mind on human happiness, on the study of psychology and of sociology. If it were up to me, I wouldn't let a single first-class talent go any more into physics or chemistry.
Where would you put them?
Into psychology.
So despite Gabor's warning that the physical research was at an end, John Hopfield continued to conduct physical research, although in his case it was at the intersection of physics and brain function. And in 1982, Hopfield proposed this Hopfield model for associative memories. Shortly thereafter, Dimitri Psaltis and Nabil Farhat built a Hopfield model in an optical system, as is shown here. And then, I had the honor of working in Professor Psaltis' group at Caltech, and was a co-author on this paper in 1990, where we drew out the analogy in more detail than the work that Van Heerden had done 20-some years before, and showed that we could create synapses in holographic associations and then build nonlinear optoelectronic devices that could act as neurons. The patterns you see at the right are fractal patterns that we needed to manage the connection structure through a 3D volume. So we were able to successfully demonstrate associative learning in these devices. The figure at the lower left is a photograph of a system using a liquid crystal light valve, which is in the foreground there. to input patterns that were then recorded, and then here are names that are recorded with associations that are recorded with codes to try to build a Hopfield memory. There are two basic problems with this architecture. One is that the Hopfield memory itself has a famously low capacity, and the second problem is that you use this holographic recording and sequence to record patterns in a volume. The dynamic range of the hologram drops in proportion to the square of the number of holograms you create, which was published in this paper that Professor Saltis and I wrote in 1992, showing that this decrease in the diffraction efficiency of a hologram in proportion to the square of the number of holograms recorded. So again, the idea of holographic associative memory kind of went into hiatus, in this case for another 26 years. But in 2016, Professor Hopfield and Dmitry Kortov published this work showing that, with appropriate nonlinearities, Hopfield networks could regain very high memory capacity. And so I won't get into the details of that work, but what's the point, one of the major points of this paper that Greg Nero and I have published is to show that this architecture, the kind of nonlinearity that you need to create a dense associative memory or modern Hopfield network can be achieved with a multi-stage volume holographic architecture. So in this case, we assume that we record an association in the input plane between a pattern that we would like to create in the associative memory with a code, and the coherent laser comes in here with a code. This is an image of the system generated by Gemini, so it's kind of a crazy looking image, but the basic idea is correct that the code is represented by a one-dimensional pattern that goes onto a optical address spatial light modulator in the middle layer. The code is nonlinearly processed and retransmitted to reconstruct the associated memory. Now, again, with this work, you have to assume that novel new technologies are developed. In particular, we need the image plane, the input, to exist as a coherent wave field. So we imagine in this paper that we have a optically addressed focal plane, so that the incoherent image comes into a photodetector array, and then that photodetector array is read out in parallel by a coherent probe beam. This addresses really the core bottleneck in modern imaging systems, that the basic function of a modern camera is to turn the massively parallel optical input into a serial electrical signal. That's not the way biological systems work. Of course, the visual cortex is highly parallel with more than 1 million channels potentially fed into the cortex. And here we're imagining that we can build a similar parallel interface that has a incoherent detector array and creates this coherent wavefront that we can then process in our associative memory. So now we have this associative memory, and we're going to build the modern Hopfield network. We're imagining that the input plane is spatially distributed. It may not be an image, it may have been pre-processed in the detector array into some kind of feature map, but it's still a two-dimensional distribution, and that two-dimensional distribution is associated with a one-dimensional code. So what's shown at the left here is the Ewald sphere, the collection of wavefronts of the input wave and the output wave on the wave normal surface. So the blue dots at the top, those are the input features of the that are detected in the image, and then those are associated with that red line at the right, which is a code in one dimension. And what this gives us is a system without Bragg degeneracy, so that the connection between each point in one dimension and each point in the two-dimensional plane is unique, and so that there's no Bragg degeneracy that would cause us to need to use a fractal sampling grid, and we can have natural image distributions that we process in this associative memory. So multi-stage holography resolves the capacity problems of Hopfield networks and allows us to create dense associative memories with volume holograms, but it doesn't naturally resolve the holographic control problem that I talked about earlier in this video. That problem is illustrated here. We look at a photorefractive material in this blue box, and then the blue dots correspond to charged donor sites. So when a field illuminates this system, in this case, we show a sinusoidally modulated intensity of the field. The red would be the intensity of a pair of plane waves interfering in the material. The plane waves, or the field excites a charge. That charge naturally migrates to where it's no longer excited, so it migrates to the nulls in the field as shown here. So you create a space charge field that's proportional to the gradient of the illuminating intensity. The problem is that after you've created this space charge field, if you illuminate with a uniform intensity or if you illuminate with a field at a different spatial frequency, the space charge field will relax because the charge will again be excited and will migrate back to relax the space charge field. So what Nero and I have proposed is a novel material that doesn't allow this relaxation. So the material consists of cells. Each cell contains a set of photoreceptor sites, and then we create a space charge field in proportion to the difference in the intensity at the photoreceptor sites. But we create within the photoreceptor sites, so we create a space charge field that's proportional to the difference in the intensity that each receives. So if one site is more intense than the other, delta n will increase or decrease to correspond to which site that occurs at. But if the two sites receive an equal charge, then the net charge between the sites will not change, and so we don't get a relaxation in proportion to a constant illumination. The dynamical equation now would have a decay that could be independent of the illuminating field, but doesn't have any decay based on the current state of the illumination. So the decay term at the far right doesn't depend on the illumination. As shown in simulations in the paper, this allows us to overcome the 1 over m squared loss in dynamic range and get back to a system where the dynamic range would either be constant or the modulation would have to grow as a function of the number of gratings, but we no longer have a dramatic loss in capacity due to this control problem. We've developed we present in the paper a particular circuit that would demonstrate this effect, and in the next video we show this circuit in operation.
Hey everyone, my name is Greg Nero. Today I'm really excited to share with you a live demo of the circuit that we presented in the paper. So let's go over some of the basic components of the experiment here. We've got our power supply, which we're using to provide the plus minus 5 volts to each rail. It's not on right now, but I will turn it on later. We have our scope, which we're going to be using to monitor the voltage as a function of time of the circuit. We've got our light source, which is a 590 nanometer LED. And we've got our circuit. So let me zoom in here on the circuit and talk about some of the main components. So let's start up here. We've got our left photodetector group and our right photodetector group. If you zoom in here, you'll see that in each group there's 2 photodetectors and that their polarities are reversed from one another. So we have 2 photodetectors in each group because having them butted up against each other like this kind of serves to minimize and reduce any kind of sporadic current that's being generated from one photodetector alone in each group. So it makes the system a little bit more robust to those small changes. These photodetector groups are sharing a common node here, which is isolated from the decay line using this op-amp. The common node is also shared by the leg of this capacitor, which is acting as our memory storage device. So these are in push-pull configuration on this common node that's shared by this capacitor, and this will serve to change the voltage across this capacitor depending on the illumination conditions across the 2 photodetector groups. So we have a separate decay line here controlled by this OTA and trim pot, and the resistance or the setting on this trim pot will serve to change the decay rate, essentially. So this is our programmable decay line. We can have, in the paper, we reference this sealed and leaky data set. Whenever it's sealed, that just means we have a very, very long decay, meaning that the current leaking from this common node is very slow. If we change the resistance and make it lower, we create a much leakier hole essentially in this common node, and it drains the current faster, and that makes the memory persist not as long. It makes it decay much quicker, and you'll see a demo of that soon. It's what we've done here is we created a system where we want the voltage across the capacitor to be proportional to the difference in intensities received by these 2 groups. So to our left group and our right group, if they see a different intensity, we want to write that to memory. But if they see a constant, if this sees the same intensity as this group, left and right, if they see the same intensities, we would like that to not erase the memory. So in a photorefractive material, the problem is if you have some constant background illumination that will serve to erase. The thing you've written here, we want to have our circuit be resilient to those constant changes. So I can show you this. So what we're going to do now is kind of zoom out here. And I'm going to turn on the power supply. So I've just turned on the power supply here. So we've got plus minus 5 volts to each rail, which is good. So now what I'm going to do is show you the scope reading and how what I'm doing to the circuit at the same time. So I've got this piece of cardboard here that I'm going to use to block the left and right groups that we just talked about. So right now you can see we have a steady, almost near zero trace there. But what's going to happen, so they're seeing the same illumination right now because we have this LED, it's illuminating from the top, and I've already balanced it so that they're seeing about the same illumination. But what's going to happen if we block one of the groups? Now we're going to introduce a change in intensity between the two groups. And you'll see that indeed we see a change in voltage. And what happens if I block the left group? Right? So I block the left group, voltage goes up. Block the right group, voltage goes down. And so notice that in the sealed case, meaning that the state is persisting, we're getting, if we go to a certain state and we're illuminating with a constant background, that state persists, it's not being erased. Say we cover the left one a little bit more again, you can have fun with this and play around to get it wherever you want it to go. And we see that it persists, which is nice. So that's what we call the sealed case. Actually, let me show you one more thing. So this is a constant background illumination, but again, if we cover them both up, you can see it also persists, right? Because delta I is 0 still. Delta I is 0 here, delta I is 0 here. Good. So now what I'm going to do is I'm going to adjust this trim pot here. Let me get this in frame. Okay, I need to zoom out again. Whoops. Okay, so now I'm going to adjust the trim pot and make the resistance less. I'm going to turn the trim pot, I'm going to turn counterclockwise here until I get to a certain point where the current starts to leak through the controllable decay line. And we see now we've configured the decay time to be a little bit shorter. So now what's going to happen? If we block the right group here, again, we see a right, but now what happens? We see that it decays back to this baseline 0 much, much quicker. So now let's try covering the left one, and we see a similar behavior. So the circuit allows us to control the decay time by adjusting the trim pot resistance, which is nice. All right, so I've showed you, this is the leaky case where it's sort of leaking back to 0 more quickly. What we did before was the sealed case. And again, you can have fun with this. So now one more thing I want to show you is I'm going to turn this back up to the case where it's maximum and adjust the light level to be much, much brighter, like this. So now I'm going to show you what happens if I cover up the right one. See how the slope of the change is much, much quicker, right? Very sensitive now. And it went very, very negative there. This is just because delta I, the magnitude of delta I is much larger now. So again, it's sensitive to this difference or change in the magnitude of the intensity too. You'll notice it's drifting a little bit more here too, which is because actually getting these two detectors groups balanced is very difficult. So if I move the light source a little bit this way, you'll see it decays. If I move it a little bit to the right, you'll see now the right one's getting a little bit more than the left one, or vice versa. So actually getting this balance to be 0, it's very sensitive. I pre-balanced it for the video, but now I'm showing you how you would actually balance it in real time. So very sensitive. Yes, and one other thing, so what I just did now is just auto-focused on the circuit, and you see that the what I'm guessing is happening is my cell phone is emitting infrared radiation to probe the scene, and it's actually being picked up by the photodetectors and changing the delta I of the received groups. So it's a very subtle change, but I think you can see it. Let me change the setting here. You see a little bit better. So again, all I did there was just sort of autofocus on the circuit, I'm not doing anything else to the system. I'm just kind of tapping my cell phone screen where I would want to focus and adjust the dynamic rate or exposure based on the illumination of the circuit, and you see that it's changing based on how I move, based on how I do that. So that's a demo. I hope this gives you an idea of how this circuit works and how it operates, and thank you so much.
I imagine that this paper, raises more questions than it answers, but hopefully we're a lot closer to actual holographic processing than we were with the speculative ideas introduced by Van Heerden in the 1960s. As you see, people have speculated for 70 years that there's some sort of link between wave propagation and biological processing. What we imagine is cameras that bridge the divide between the current pixel time, frame-based model of how we capture media and the biological model of the visual cortex. We're really excited that we think we've made a step forward with that in this paper, but we recognize that there's still a lot more work to do. In any case, if you go to the archive link shown here or in the description, you can go read the paper yourself and understand what we've done.